I want to do it in terms of the numbers. It'll be so much faster. Yeah, but now like simplify everything down.
Field to go in. This is analog.
Yeah, I mean, because
So it's
Okay, let's get started. Let's see, announcements. So the homework 3 solutions have been posted. The data sheet will be posted tonight. I'm gonna try and get done by 5 o'clock. We're having people review it. We'll have office hours tomorrow from 3 to 4. I suppose if there's a lot of people, we'll try and find an alternate room, but I'll post a note on the door if we do move. And then the exam is gonna be this Friday at 4:30. Down, so it's just down the hall, like go all the way down that way into Beister, and it's the big, not conference room, but classroom over there. Okay, any logistics questions? I mean, we're gonna go through exam logistics, of course, but any other logistics questions? Nope.
we're only allowed to do only that, right?
I'll go over what you're allowed. Okay. So today we'll do exam logistics. I'll do a quick kind of overview of course content. Mostly this is like an invitation for you to ask questions. So if something I've made extra confusing or was confusing for you the last time I presented it, they're kind of gonna be the same slides. It's your time to ask questions, right? And then we'll spend probably the second half of the class or maybe a little less going over a practice problem. All right. So midterm logistics, we know where it is. It's closed notes, closed books. You only need to bring a pencil. You can bring a 4-function calculator. You're going to be provided with the data sheet and the reference sheet and everything you need. So there's no paper material you need to bring in. No graphing calculators, because guess what's inside of them? ARM processor or something similar, right? And certainly people can go make an emulator for ARM if they really wanted to. So we're not going to do that. No phones, keep them in your bags. We'll make sure that there's some sort of timekeeping device available for you. I mean, obviously, if you have a watch and it's not a smart watch, go for it. I suggest bringing a ruler. There's one problem where you have to do a small amount of drawing. You might want to, you don't have to measure anything, but you just might want a straight edge. You could also use your student ID. So you probably already have something in your wallets or purses that will work. Okay. Now that we've talked about what you can bring, are there any questions? All right. General, like just good test taking, like don't spend too much time on the problem. This is the goal should be optimized points returned, not, you know, if you find 10 or 3 points and you're spending a lot of time on the 3-point question, just ignore it, go on the rest of your test. This is, you know, this is a expected optimization sort of problem, not a get everything correct problem. State your assumptions. You know that we're getting to that point in your career where there's no longer correct answers for things, right? The embedded systems is a trade-off between different factors, and we're trying to expose these trade-offs to you in the exam, and sometimes that leads to ambiguity. Well, you guys can obviously come and ask us questions, clarifying questions, or you can just say, I assume this is true. And as long as that's a good assumption, you can't say, I assume the answer to all my questions are going to be A. That's not a good assumption. But if you're like, oh, this data bus looks weird, or I don't know, the logic, it's not defined what the logic is. If it's logical high or logical low, to say I assume logical high, and then we'll have to accept that, right? So that's one way to deal with some ambiguity on your test rather than getting really stressed out or coming talk to us. But you're always welcome to come talk to us. Let's see. Show your work. to explain what you've done, especially with some of the design problems. It's nice if you're asked to write some code or think about something, just tell us what you're going to do. Write one sentence about what you think you're supposed to be doing instead of just launching into code. I can give you credit for that. It's hard if you're like, just code goes crazy, and I'm like, I don't know what you were doing. Right? I don't even know what you intended by that. So think about ways to demonstrate your knowledge to us. Let's see. Getting partial credit without showing work is rare. How would I give that? If you just throw me a number, 42, I don't know how to do this. Yeah, data sheets. Okay, so the data sheets will be made available tonight. You're welcome to discuss them with each other. How am I going to stop you? You should, if you have questions, clarifying questions on the exam or on the data sheet, post them in Piazza so everybody can benefit from the answer. If we make any changes to the data sheet, we'll post it in Piazza that it has been changed, and we'll update the data sheet because it's in Google Docs. We were not going to make any changes to the data sheet like in the exam. Obviously, that's not going to work. And we'll try and lock it down like, at least that Friday morning or something, or Friday midday, so that you don't have like a surprise change that's going to come up on you. All right, let's see. What to study, homeworks, labs, some old midterms on the website. Yeah.
Old midterms from like your previous year's teaching class, or they're just old midterms from the class?
There were some of them are mine, modified, helped out. Sometimes it's a group effort. So I guess the statement would be, do you expect to have exactly the same types? Pretty close. Yeah, I'm not trying to generally trick you or like say, do you remember that part of the ISA like deep down? And like, that's not, bringing up some esoteric facts is not useful. I know some people grade that way, right? Especially when you have really big classes. Right? They're like, the students who know the most are the ones that memorize the most insane facts. I'm not sure that's the learning outcome I'm hoping for. So try and keep it kind of big picture. Yeah.
Are we expected to have the data sheets printed for the exam?
I'm going to give you everything you need. You just come with a calculator, a student ID, pencil. Yes?
It's going to be a problem if we don't have a calculator that matches those requirements.
I don't think you need a calculator.
Okay, because I don't have a calculator, so.
You're going to be okay. I mean, the calculators are useful. I'm bad at math.
I have one on my phone.
That is not a calculator. That's a phone.
My phone from TID4.
Nope, that's not a thing. That's not. Yeah, you can't use a graphing calculator anyways. And that's an ARM, that's an ARM something on there. That processor. Right? It's an iPhone at least. All right. Anyways. Okay. These are the main subjects we're going to cover. I'm going to go over some of them. You guys are welcome to stop, divert this conversation, ask any questions you have, okay? I'm going to go, so the first slide is going to go off in left field for a few slides. Don't freak out. I realized we never actually talked about, what are all the pieces of the instruction set. Generally, this was covered in 370, but there are nuances here, so I figured I'd at least show this to you. I'm not asking you to be an expert at decoding random instructions, but there was enough questions about it in office hours and other places that we figured, okay, I'll just remind you of how these things work. All right, so you got a label. This is the memory location. You got a mnemonic. You got a destination operand, source, second source, or some other modifier, and then that would be your comment. Okay, so how would I go through and figure out what the heck all this data sheet means? There's actually a lecture on this on their website. But how do you decode this nonsense? So we got some mnemonic here. You've got the S, sets the conditional flags. So if you add that optional S, the result of this instruction will set the conditional flags, which then you can do conditional branches on, or compares, or other things based on those conditional flags. This is to enter if you wanted to have conditional execution in an IT block. We don't really discuss IT blocks in this class. They're great for compilers. They're great for making case statements, not real subject matter for this class. This is if you want to define in this particular add. This is if you want to define that this is a wide instruction. You can say that I want to specifically denote that it's going to be wide, regardless of how the compiler interprets it, if that makes sense. So you get to instantiate that you want the wide version by putting the .w in there. Destination, source operand, second source operand. Shifts. So part of some of the instructions, you also have the option to shift information. So you can shift by a constant. They'll tell you the type. They'll tell you how much shifts to do. So buried in this, if you like down here, would be all the things that go in the instructions, and one of them is this standard modifier thing. So you can read through the data sheet if you really cared to understand the details of it. But that's what it's for. When you see that in some of the instructions, this gives you the option to do bitwise shifts as well. Any questions? Yeah.
Where does the 0, what was it, parenthesis, like the one on the 15 bits, do again?
I don't know. It's 0. It does 0.
So like no specific meanings, like just 0.
I remember I looked it up long ago when I first was learning about the ARM instruction set. It's buried deep in the documentation. If you find out, let us know. Any other questions? Yeah.
So for the shift, does the value go in those 2 bits for type, or does it go in immediate 3?
Let's see. The shift goes in. So the shift is here. So here's what you're telling you the shifts are. So the shift is the type of shift. So if you go through documentation, you can like shift left, shift right. I don't know what the other. I don't know why they need 2 bits for it. Probably to enable, and then I don't know, to go plaid. I don't know what 1.1's going to be, but it's going to be something. And then these are to denote, yeah, the immediates for the shifting. And so it's helpful to kind of like figure out how to read through these cryptic comments. Again, this is maybe, I'm not going to ask you like what 0 mean on the test, and it's unlikely you're going to have to like remember what set flat, well, you will have to remember that. But like decoding every little bit in here is probably not important. But understanding generally what those fields do, and if you're asked to encode a question, instruction, how would you do it? That would be important things to be able to do. All right. Yeah.
So I think in one of the homeworks we had a question when the constant value was given in 5 bits, and then this diagram showed you only IMM3 and IMM2. Do you like split it? Just you take the 3 bits of the 5 bits of the immediate value and split it out.
Pretty much, it's telling you, it shows you what the concatenation is down here. So it could have gone and put that over on that side, so it's like 2, 3. I've never seen that in the data sheet, but they're giving you that option. Sometimes they break it up into 3 sections and they'll show you what the concatenation looks like. But that's where it's defined.
And is there any reason they do that? They don't stick
Oh, I'm sure the architects went through and like figured out this is the optimal to reduce the number of gates in my thing, and that's great. They have good reason. I don't know what it is. I'm just living in their world.
So, like, let's say we were doing like an immediate value of like 5, for example. Does it get split like from the first 3 bits and just the last 2 bits into the instruction?
Here?
Yeah.
Yeah.
And it's like left 2 right?
Yeah, I was telling you that they're concatenated this way. So 1 place, 2 place, or 0th, 1st, 2nd, 3rd, 5th. Yep.
What are the APSR flags?
What are the, what flags?
APSR.
Where do you see that? Oh, APSR, that's the application-specific flag. So part of the application status register is broken up into 3 sub-registers. One of those registers represents the results of the ALU when you tell it to update. The way you tell it to update is, I want you to update when you put an S there. Yeah.
Oh, where would you go to see how to, or what the bits of type correspond to shift?
About here, it says something like, this uses the standard shift blah, blah, blah thing, and then it's usually a hyperlink, and then you link to that, and then you like go and read what that is. And I've, at this point, have forgotten that, so every time I go to it, I just click the button and remind myself.
And we'd only use ARM7 or like thumb if we're trying to save memory, like in terms of like not.
You might say that the smaller encoding, right? So the 16 encoding, Yep, that's true. That's primarily there to save space, program space. So ARM claims that they're like, can get like, I don't know, I forgot what the number was, like 87% optimization by going between 32 and 16-bit instructions. I'm like, okay, and then I don't know how they figure that out, but that's their claim. Okay. All right. It's super important. At this point, you might have been running to these to death, but it's important to understand the register space in the core. We have the lower registers and upper registers. Why do we denote that there's lower and upper? Why does that matter?
Because 16-bit instructions can only access the lower register.
Correct. Now, it's probably not, we could construct in our brain some sort of 16-bit structure that could make it all the way up there, right, to access those registers. This is just the delineation that ARM has made. 16-bit instructions go for the lower registers. They're more common. You're more likely to manipulate things in there. Therefore, we're going to compact storage space of our program. If you do need to go in here, generally it's going to be a 32-bit instruction that will allow you to access these upper registers. Field questions? No question. Yeah.
Oh wait, so if that's a thumb, so the R8, the R13 to R15 will still also be used for link register and for special register. Are they also going to be used in the sum? Only the 0 to 7 register.
I guess we'd have to look through this. Sorry, I bet we could look through the thumb encoding and say that you could do a pop with 16 bits, and that certainly involves the stack pointer, right? And you can probably do a no-op and advance a program counter. Like the instructions can operate here. It's just if you want to do something like add two numbers together, and one of those numbers is an R10 and the other one is an R9, you're probably going to have to use a 13 or a 32-bit instruction because there's just not enough space in a 16-bit instruction to encode this, right? Of how many, just the number 9 needs more bits than the number 5. And so that's the optimization, is how many bits can you cram in that instruction. So it's not like a thumb can't run a processor. Thumb instruction can, it's just going to take more instructions. I guess that's the trade-off. If you did everything in thumb, then you need lots more instructions. A 32-bit instruction is more expressive. It can get more work done in one clock cycle. So there's the trade-off between size and speed. Okay. What other questions? All good review so far? We talked a little bit about the main stack pointer and the program stack pointer. Don't worry about it. Just know that there's a difference. When you're debugging your horrible code in lab and you see this and it's confusing to you, just remember that it exists. But for exam, we're just going to assume that it's going to be just the stack pointer, or that you're always in main stack pointer mode. Okay. Oh, we didn't talk about the specialty registers. It's really the program status register. These, like the base priority register and some of these other ones, will be more important when we talk about interrupts for the next exam, but this is the program status register that you really need to pay attention to. All right. All right, so we have inside the core, we have registers. Outside, we have memory. So I think the big piece that I want to make sure that everybody remembers, well, first is that who came up with this plan? Why is it like this? Why do we have code always here, SRAM? Why is it like that?
Makes it consistent across a bunch of different, the interface is consistent all the time. And if we need to add stuff, if we need more SRAM, we can add more SRAM into this already predefined space for it.
Yeah, and I think it's part of that is just remembering business models are affecting technology. It's weird to think that way, right? It's usually you think technology should live on its own, and then you should always choose the best technology. That's what we're kind of taught, choose the best answer. And now we're in the world of, oh God, the business people are in charge, and now they're telling us what architectural choices to make. Yep, it's painful, but essentially this is a construct of the business world saying, I want to make a platform, the software for ARM's processors that can be used by everybody, and so they just make this allocation. Okay. All right, the other one that's constantly confusing, and I don't know how to teach it in a better way, is that, so ARM has allocated memory that is byte addressable. So every byte has an address. However, it's a 32-bit architecture. We don't think about every address just being a byte. It's not how we use data, right? Everything is pretty much going to grab 32 bits out of memory, you're going to put 32 bits in memory. So even though it is byte addressable, it's important to notice that we're going to use word operations typically to get data in and out, and therefore memory in that case would advance every 4, right? So you're going to load data into whatever this, A1AC, you're going to load in, and you're going to load in 32 bits instructions. It's going to go, or 32-bit word into there, and it's going to go from the lowest up to the highest bytes, replacing that entire word. How would you do it if you just wanted to replace a single byte? What's the way to do that? What?
Masking and shift.
Meh. Byte instruction. So yes, there might be some masking and shifting based in how you get there, but how you store information in just to a byte would be the byte instruction. So store byte or load byte. You can also do store half word, store or load half word. And those are still into individual addresses that are byte addressable. All right, did I make this confusing enough?
So each of our instructions, mostly the half word, or all the 16-bit instructions are half words.
Correct.
2 bytes to get the instruction.
Yes, however, we did review this. I mean, it's buried in the knowledge of this class. When we're fetching an instruction, we're always fetching a 32-bit word.
Okay.
Because how would the processor know, oh, I'm only supposed to get 16 until it decodes it?
It doesn't know if it's a 16.
It didn't decode it until it has it in there. So it always gets 32. It looks at it and starts decoding it, and then it says, I have 2 16-bit instructions, or it has 1 32-bit.
I forget if it's like the first 4 bits. Doesn't the processor know that it is a 32-bit instruction or 16-bit instruction depending on the first 5?
True, but how do you, yes, so it's the first 5 bits that encode, or it's 32-bit or 16-bit, but in the fetch process where you're loading something from memory into the core, I mean, load is the wrong term, you're just taking it 32 bits from memory, program space, and fetching it and start, how do you know to fetch 16 or 32 bits until you've decoded it? You have to get it into the processor for the decoding to happen. You're not decoding in memory. So then you're always pulling 32 bits, look at it, figure out what your instructions are.
So you might be taking either 1 32-bit instruction or 2 16-bit instructions?
Correct? Or the job here, right, the fetch operation is just like a truck. It's just I don't know what I'll have. I'm just taking data over here. The core figures out what it's supposed to do with it.
Remember the load word and load byte for MOV? Which of them?
MOV.
Which? The MOV instructions in registers for assembly. There's a MOV W. Is that for?
Move.
For? Yeah. MOV. MOV W. There's no E at the end. Yeah, you MOV it.
Okay. Super good. Okay. What's your question?
How many of the registers does it pull at once, and does it account for little or big endian?
When you're pulling out of memory, so move doesn't work on memory.
It's not registers.
Yeah. The only thing that goes, right, why is this called a load store architecture? Because the only way the core interacts with anything outside of the core is by moves and stores. So all moves and move Y, that all happens internally to the core. Yeah.
What's the difference between move and
Move and load. Load and store are going external to the core, to memory, and doing an operation. Move is from registers, one register to another register, or move in immediates. Good questions? Yep.
I have a question about the stack. So when the stack pointer, when you run a pop instruction on more than one register, does the stack pointer, it increments by that amount times 4, right?
Correct.
So it, like if it started at 0, it would end at 8 for the 2 registers.
Correct.
Okay.
Right. So that's, again, everything's set up to work at 32. Memory addresses are size 32. However, we do have the option of going byte-wise. So that the caveat, you're right, is that everything's going to be memory effectively increments by 4, except when you're trying to do bytes and half-word stores and loads. All right. That's good questions. Let's see. So bring this up to, this is the mental model you need to kind of build is like, how do these 3 things interact, right? We have register space, we have memory, we have some program, you have the program status register. How do all these things interact? And once you have a good mental model of this, you know, I think that's a great place to be for this upcoming exam. So really it's, how do all these things interact? Where's your code? What's your code? So move is only in here, load stores are out there. And then how does branching, decision-making happening really with the program status register? Any questions? I didn't provide any information, but yes.
Be tested on the Q flag.
In your reference sheet, it tells you what the flags are. I mean, it should. I don't know.
Well, the reference sheet that I saw, at least for like the maths exam,
Yeah.
only gave us N, Z, C, and P.
Yeah, there's no Q.
Put it in Piazza, and I'll add it right to the thing. Yeah. Yeah.
Are you gonna add like an Indianness diagram to the reference sheet, or should we memorize that?
I should memorize that. That's a good question. I can't put everything on there.
You could.
I could, but you know how big the reference sheet would be?
It'd be like
It would be like I just hand you the manual and say get to work.
idea. The PDF, your computers.
Oh yeah.
Wait.
Then I get to ask even harder questions. I say, assuming that you have the Cube IDE installed, let's go to town.
It's just a lab.
It's timed lab. Oh, this is fantastic. We should do that. That's fantastic. Timed lab. Okay. Yeah. Yeah.
Oh, if we want to move the value of one register to another, do we have to use the 2 move instructions, move T, and then I can't remember the other one.
Move top. No, you can move run register to another register. It's when you're trying to do immediates. You can't move immediate because a 32-bit immediate because you don't have enough space. There are some special caveats because like -1 and some other numbers that they'll give you for free. The compiler will do for you.
Let's say for like the move instruction right here, instead of saying like move R0, immediate 1.
Yeah.
We change it to like move R0 and like R1.
Right.
And what would be the difference between that and load R0?
Load is getting. Where does load get data from? Right. Where does move get data from?
The register?
Right.
Oh, I see. So it's the difference being is where they get the information.
Yeah. I mean, and it's also like, so they could have probably just overloaded that instruction, right, and said like move everywhere, but it makes a very clean conceptual break, and there's hardware implications underneath. That even though they essentially do very similar things, one is only for working externally, the other one's all internal. We talked about the scary diagram. Should be getting less scary now. What are the things? I think understanding how data flows, I forgot what my builds are doing. No, understanding how data flows through this is important. There's some details that are probably like not really covered in this class, like what's the advanced high performance bus matrix? Ooh, it's actually pretty cool. That feels like advanced computer architecture. It's basically a way in which you can have multiple destinations and multiple sources running concurrently. It's like a mesh that gets programmed by the core and some other stuff, not by you in the core, but like by the controller to send data around. You don't need to know that. The details of how the data bus and instruction bus work, and the I code path and decode path, not important. You just have to remember there's a whole separate path for how data and instructions get to the core. When we talk about loads and stores, we're not on that, even on that same bus. We're going through this bus structure. And really, so far we've talked about the H bridge to PB bridge. So this bridge has been the initiator, and those have been the peripherals or the targets. We haven't really talked about the high performance bridge. Again, it's interesting. It's just not an important detail, I think, for understanding how the whole system works. Any architectural questions? Yeah.
I have a question that's unrelated. Do we have to remember the post offset, pre-offset, that syntax ourselves, or will that be on the data sheet?
You can post a request to Piazza. So I haven't even posted this sheet yet. I will give you, I can imagine, if it's not on there already, some nomenclature like the instructions already there, but I'm not gonna like give you a tutorial on what you should have already learned. So if it's just like, oh, I kind of forget it, yeah, I can add some instructions on that. But I mean, I guess, let's look at it a different way. You will probably be asked to do something with instructions, loads and stores and offsets. It would benefit you if you were fast on those. If you knew exactly what to do, you saw the problem and you were delivering. If you have to go, oh my gosh, I hope it's in the data sheet, that's time wasted, right? Speaking of which, bam, there you go. Post-indexing, pre-indexing. Pre-indexing, I remember this by saying, look, so here the brackets represent memory. And so pre-indexing is the data is, or the offset is in the bracket. Post-indexing is the memory representing the bracket, is the offset is after the bracket, so it would be post-indexing. And then pre-indexing with updating is bang, right? It's like here, we're gonna do it immediately, do it now. So that's my mental model of how to do this. Any questions about post-indexing often? Yeah.
And this can be applied to like stores, correct? Same way.
Sure, yeah. All right, and then you can have negative numbers. Okay, oh, here's an example, here we go. So pre-indexing, had 4, so you've offset. So here you have some value in the register. So we're gonna take the address that's in R, is represented by R0, we're gonna take the value there and gonna put it into R1. We're gonna add 4 to it, and then we're gonna move that into R1. All right, any more questions about loading stores? Okay. Application of binary face, color stacks. Let's see. So we think about it's important to remember which registers are scratch space, which registers that as a function you are responsible for storing. Right, let's be careful about R12. Yes, R12 is also reserved as an in-there procedural register. We don't really use it in this class in that context. It's usually for the compiler or for interrupts to pass data back and forth through. So I would be a little bit careful with that one. You probably will not need it for any of your exam. Or I would just be careful with that one in general when you're writing assembly. All right, arguments are passed through R0 and R3. So the assumption is the first variable in the C function would go into R0, the second into R1, and so on and so forth, and that you're going to return data in R0. 64 bits would be across R0 and R1, and then it would be up from there, right? So if you had 4 variables, you can go up to R3. If you have more variables to return than this, what's a way to do that? You have to, 10 variables you have to return, or 5 variables. What are some methods?
Put them in the stack.
Could put them in a stack. Yeah.
You can store a pointer.
Right.
Return a pointer.
Right. You can go put them in memory. Tell them where it is in memory. I don't think there's any other amazing ways. Put them in a heap if you wanted to. Haven't really covered that in this class. Yep.
What's different putting in memory versus putting in
just whether it's allocated dynamically or the memory's already, like what's the space basically? Like what's it used for? Okay. Oh yeah, we did discuss this. Yeah, R12 is the inter-procedure call. R9, you can just use it for most versions. You can just use it like a normal normal register that you have to protect if you're instruction. These are the scratch spaces. All right. Oh, Jesus.
So for calling saves, right, where you'd only save those registers if you're in a function that gets called.
I save. So say I'm calling a function, I'm responsible for retaining this information if I need it.
For R0 to R3? Or
Yeah, if I need that information, there's no guarantee the function is going to return these things in any known, with any value in it that I care about. Does that make sense?
So, let's say if I'm in main and I call a function foo,
Yep.
and then I go into foo, foo needs to make sure to push R4 through R8,
Yep.
and the linker, the link register, and pop everything once it's done with what it needs to do.
It doesn't need to store the link register. The link register should have been updated when you branch to the function. It's only if the function calls a function.
Oh, I see.
Yep.
So to clarify that again, so if main, or if foo was called in main,
Yep.
then the main has to save R0 to R3, as well as link register.
Main is not required. It's not as if main has to push these up. You're in this thing. It's just you can't guarantee that the function is going to return your variables in here. So say you want to pass R0 to a function, but you had some other really important variable on R3. The function can go and clobber R3. That's ABI compliant. So if that's the case, and maybe you just didn't have enough space over here, in that case, you're going to have to push R3 to the stack, call that function is whatever it was, returns to you, and then you can pop that value back into R3 so it's there for you.
Okay, so then for registers R4 to basically all the ones are in red.
Yep.
Then if there's important values in those registers, then do I push it in main or do I push it in foo?
So main expects that these values will not be touched, will not be altered. So then it becomes the function's responsibility, if it needs these registers, to return them to their original state.
Okay, gotcha. Thank you.
Yep.
So then we don't, let's say we call a function from within main. We don't have to push R4 through R8, but we do need to push R0 to R3.
So you're the function?
Yeah.
No, you don't have to. This R0 through R3 is your scratch space. You can do anything you want with it. If the thing that called you put special data in there and you clobbered it, that's main's problem, right? Main should have taken care of it.
So for push, you said there wasn't like a specific order we had to list the registers in.
Correct.
It just knows like.
Well, say it another way, if we go look at the encoding, the instruction encoding for push and pop, it doesn't retain the order of the instructions that you put it in there. It just says, oh, you wanted R0 through, it will have fields, bit fields for say R0 through, I don't know, R8, let's say, or R7. So it has 8 bits, and it just puts a bit with what thing should be pushed or popped.
Okay.
So it doesn't know what you intended. It just looks at this instruction and says, I got to do these things. So it says, well, I'm going to go by a convention, which is always highest register first.
Okay.
Yeah.
That is, if we push other registers at the same time, but if we push them first R5, then R4, then R7, so with different instructions.
Yep.
The other is the other that we set.
Nope.
No.
Absolutely not. Because think about this, kind of back to that point. So if you want, so let's back up to a different condition for a second. If you want to preserve the order in which you pop things, just do it as or push and pop. Just do it as separate instructions. And the compiler will just say, okay, I'm just going to do each one sequentially. If you want to optimize and push and pop more than one thing in an instruction to save program space, then it's whatever order, then it's the order defined by the highest register first.
So if you do it in separate instructions,
Yeah.
you define the order.
Yeah, you define the order. Okay. Let's see. I guess we could have gone through this example. Let's see. We're going to be doing sum of squares here, showing you from C that your variables are going into R0 and R1 that you're passing to the function, and your function is going to return them into R0. And so we can walk through this example quick. Let's see. So first, what do we got? We got your instructions. You have memory addresses of your instructions, and then we have your registers. So these are good mental models to kind of have of how all these things work together. All right, so first our program counter is pointed at 1280 or 12.8. So here we're going to move an immediate into R0. Then we're going to move an immediate into R1. We're going to branch to sum of squares, which happens to be at this memory location. So we're going to take the instruction, the address of the next instruction here is going to go in the link register, and then we're going to branch to sum of squares. So now we're over in here. We're going to multiply some stuff together, multiply some more stuff together, add it together, and then place it into R0, which is where it needs to be when it's returned. And then we're going to branch to the link register. And so we're going to take this value and put it in the PC, and that's the end of our subroutine, and that moves us back to the end of the program. No stacks in this one, but any questions? Yep.
And we have to make sure that we branch back to our program by branching to the link register.
Correct. That's the only way you know back to where you were in the program. Yep.
Could we just always push the link register at the start of the function and then pop it as a PCA?
You could do that. Somebody might say, now, I'm not as litigious as this, but somebody might say, why are you incurring all that delay by going out to memory? Why not just do it all internally? You've cost extra cycles, at least 2 cycles to go out to memory, when you could have just done it in 1 cycle. Yeah. I'm not that, I don't care that much. I mean, I'll tell you specifically, do it as fast as possible in the thing, but I mean, I have to grade these things, right? Like, oh my gosh, sounds horrible. Okay. Yeah.
For the memory addresses, is there a reason that, so they increment by 4, but then it increments by 2? From 134 to 136?
Oh, that's just because I didn't pay attention. Oh, yeah, okay. I remember from the slide we talked about that sometimes you technically be incrementing by 2 because it's 2 16-bit instructions. And so I think in the original slides I had highlighted that as that point. But I think it's just easier to think about, let's assume even 16-bit instructions are just going to be every 4 in their own memory location, right? Because that level of optimization is kind of painful. At least to keep track of in this example. That's a good observation. Okay, and then we end. Fantastic. All right, memory mapped I/O. Can somebody give me a definition of memory mapped I/O? A brave person. Got to be a brave person to do this. You gonna try again? Okay, let's go for it.
Memory mapped I/O is input and output that's dependent on loads and stores to do everything.
Okay. That's good. We're getting there.
Defines how the processor core communicates with the code.
Yes, I like that. Yeah.
It allows us to access external memory. We can write to that memory.
Yes, but what about, you got exactly the right ideas, but what about specifically the I/O part? How would you modify your definition to deal with the input-output like GPIO IOs?
Well, you use those input outputs to access the memory. You're connecting some sort of external memory or storage or whatever.
Yeah, okay, so I think we got off track for a second there, but you're on the right track. If you want, the way in which the core interacts with everything else is through loads and stores. And it does not know that what it's doing is actually setting a GPIO pin high or low. The core just thinks it's doing loads and stores. So memory mapped IO is a way to interface, you had a good one, how do you interface with parts external to the core through loads and stores. I don't know, I'm sure the internet has a perfect, crisp definition. I should go investigate what it is. Okay. Let's see. So it's also important to kind of contrast memory mapped IO with port mapped IO. Port mapped IO meaning that there is a dedicated functionality, say a port, like you have a GPIO port, but the way in which you would deal with that port is specific instructions. So on higher end processors, maybe have a video bus or something, you'll have instructions that only thing that it'll ever do is set bits on that port or transfer data on that port. So that would be the difference. Here, memory mapped IO is, it's just loads and stores. That's the only way you get to interface with external world. Yeah, and this is just building upon that. The core is going to store some value at some memory location. It just happens to be that that will configure, control, or manipulate a GPIO pin. The core has no idea how that works. It's you as the programmer that's responsible.
And we've been basically doing this in labs, where when we press the button, that gets set over to the core.
Yes. I mean, when you like press a button and then your core does something, right, it goes back through GPIO and then your core had to go and read from a memory address to get that data. Yep.
So with the GPIO example, is there like a register on the GPIO side, or like on the STM chip at the GPIO port, I guess?
Yep.
Is there like a register there that's reading in data from the GPIO like port itself, and then we read from that register?
Correct.
Okay, so we're not reading like from GPIO, we're reading from a register that reads from GPIO.
Yes. So here, this memory space, we could just say is what the core thinks exists, but really here is a bunch of D flip-flops in a register. Those D flip-flops are going to be connected to a GPIO pin, and then you push one into this memory address in this particular bit location, and something else happens, which is a pin going high. Which is why here we go, we did it. It's exactly that example. We can imagine here that, so this is a port B or so, and it could go off into as many pins as there are, but now we're just going to concatenate. So reg in is going to be a concatenation of all those registers, and when you say read out of port B, whatever that memory location is, you're going to pull in the bits out of those registers, and you're going to look, is this particular bit in this memory field a 1 or a 0, and now you know if somebody's pressed something. And this is like a mock version of what you'd see in the data sheet, right? Like there's some address with some bit field, and in this particular case, like this is the 0th bit that controls this imaginary control register. Right, and so you want to set this to an input, you set it high or low, or whatever the logic is. No questions, okay. Yeah, okay, good, thank you.
Okay, so with this, there's no way to set two external peripherals to access the same memory, or like memory address. And I can't have GPIO A and B both linked to memory 33088.
So like the input is not going to, you're not going to have two GPIOs going to this location.
Yeah.
That would not make sense because now you have a conflict. But you might have GPIOs like PB0 is going to go in the 0th bit, PB1 is going to go in the 1th bit.
So there's no way to force it to put two peripherals in the same address.
No. What would that be? Maybe I'm missing something.
I don't think there would be a good
Okay.
way to do it. I'm just curious if we could.
Nope. All right. What was I gonna, oh, this is just a further, like, to make it super clear how the path goes, right? You have some register bank, you're going to store information, it's gonna go through the system bus, and then the AHB matrix, and then it goes to the bridge. And this is where you guys kind of pick up here. You go from the bridge through the bus structure to that GPO, and then eventually a one goes out, right? So there's a lot of different steps in trying to get the data out of the core and onto a GPO pin. And those steps, yep.
Is this the FPGA in lab, like, is it connected via GPIO, or how is it connected?
So we gave up, we used to have a chip that had an FPGA and ARM Cortex M3 in the same piece of silicon, and then you wrote your own peripherals. And all the architectural professors were so happy. So they're like, aha, we're doing architecture. And all the students were confused because the tool chain was horrible. And so the compromise was, we'll go to a more modern processor, a more applicable to most of the things that we do. That in lab, you were on a bus structure. So that bus structure is being exposed through those GPIO pins, and you're supposed to be connecting. You're making a mock peripheral that's technically off your chip instead of in your device. But you're on a bus. It's just a slightly different memory bus than this particular bus structure.
So pretty much our FPGA is connected through a GPIO pin?
It better be. I don't know how else you're going to get it in. That's the only way to get data in and out. That GPIO pin has been remasked or connected to a memory controller bus, okay? And so that is essentially, you're saying your FPGA sits here, and there's a bus structure that can talk directly to it. And so you're doing a mock peripheral. It's just that we have to do it externally because we didn't want to invest in this very complicated chip. Yep.
So I think the original question is, we're bypassing the GPIO peripheral to use a separate peripheral?
Yes, you're reusing the pins.
Yeah.
So yes, I did not catch on that detail. So basically the difference here is the GPIO pins are a path in and out of the chip, but you can take the data path and send it to other parts of the chip. So you can, as you'll find out later, we can use general purpose I/O pins for things like ADCs or UART or memory controllers or all these other functionalities. You're just routing it essentially past the GPIO input and output pins, or at least the input pin to somewhere else, or the output pins to somewhere else. That was a good question. What other questions do we have? Okay, part of that is we got to know these timing diagrams. You have to understand how data is effectively, in this class we're obfuscating that the bridge would be right next to the peripheral, or right next to the core. It's not, but that's okay. For the purpose of this class, we can just assume we only care about that little bit. And there is literally a mechanism, signals wires that are pushing data from one location to another location. It's important to understand what that signaling path is. It's important to understand this diagram. Where are the big pieces to remember here? Oops. Big piece to remember is that there's initiator or the APB bridge. It has multiple targets or peripherals. There are some signals that are common to all the peripherals, right? You don't want to have separate wires for everything. So like write data goes to all the peripherals. The address goes to all the peripherals. But there's certain, and the clock goes to all. But there's other signals that don't go to all the ones. So P select goes to a particular peripheral. The outputs of the peripheral are all unique, so trying to think about avoiding bus contention. So you have 32 bits read data path. There's a unique bus just for that. There's another bus for target 0, and then P ready is a unique bus. So there's no bus contention on the outputs of the peripheral. That's just not, by design, they're making sure that doesn't happen. So it means there's hundreds, if not thousands, of wires going into the bridge controller. So it's a lot to keep track of. This should generate questions. I promise I'm not that good at teaching.
write data, the address that you want to write to, just the P address, right?
Sorry, P write data.
So yeah, the data the address they will about to write to is the P address, right?
Well, when the initiator puts data on P write data, it goes to all the targets. It goes everywhere, right? The bus is connected to everything. The only peripheral that should care is the one that's selected. Yeah.
What's the difference between double wire and single wire? Is it just because it's more bits?
Yep. So I'm trying to note this is 0, this is 32 bits, this is single bits. It's just giving you a visual indication that it's a bus rather than a line. Yep.
I still don't understand the idea of P ready always being held high. Like for multiple of these targets, would it still be reasonable to say they're always held high, or would we need to actually have each of them go high at different times?
So in the real world, there's a bunch of extra logic that's not important for you to write down in an exam that's going to say when this thing is done with its task, it's ready to be read, the pin is going to go high. It's this response to talk to the initiator. Another thing to think about is that these two are often on different different clocks that may not be multiples of each other. And so by doing this kind of handshaking where you say, okay, the data really is ready, right? The data now is ready. That means the next time this thing clocks, its clock goes by, it knows to grab it out. So it's also a synchronization method. And now I forgot your question. I got off on topic.
Like I'm thinking kind of the last question on the previous homework where we had two different things that
Yeah.
we were talking to.
Yeah.
But there wasn't really any way to figure out how to set the P ready besides just leaving them both high at both times. So does that mean that the initiator?
Oh, P ready, sorry. Yeah, go ahead.
Does that mean the initiator would like constantly be pulling from both targets?
No, it is only when it wants to.
Okay.
Right? It's just saying that it has individual lines that go back, so there's no node connection, anything there's no node problems here. And all we're just saying is this thing has its own state machine, and after it's gone through, set up the data, set enable, then this thing has the opportunity to respond. And if it happens to be ready immediately, great. So it could just hold it high indefinitely as long as it's always ready. But if this thing needs extra time to become ready, then it needs to pull low, telling the initiator, don't pay attention to me until I pull that high. Yeah.
So how do you know when communication goes? So let's say target 1 was like ready data. How does the initiator know that? I guess I'm like kind of confused. Is it a one-way street or is it two-way?
Well, they both have their own data paths, but the only person or the only entity here that can initiate a communication is the initiator. You can't have, this target doesn't come up and say, hey, I'm address so-and-so, it's time for me to talk. It's like too bad, right? Only when you're called on do you have the opportunity to speak. Makes sense. So does that answer your question?
Yeah.
There's a question, go ahead.
So like let's say the initiator will select, let's say target 0.
Yep.
And target 0 is wanting to write data to an address.
It doesn't want to write to any address. It writes to if the initiator asks for data, it's the initiator's defining the address. This thing doesn't say, oh, I wanted to go, this thing doesn't write to any address. It doesn't have that option. It says, when asked, I will respond with a particular packet of data.
Oh, I see.
But these are all outputs and these are all inputs. I mean, there was another slide that defines this, but these are all inputs, these are all outputs. So address is only an input here, is never defined as an output. It can't output data on address or an address. The target cannot define what that is.
And then so if I select target 0, then that data gets sent to the initiator because I asked for that data.
Yeah, the initiator asked for it.
Yeah.
The target got it ready. The target pulled P ready high, and the initiator reads it out on this bus. Good. Okay. We went through this example. Basically, we're just saying here's some pound defines essentially, And we're going to say, okay, we're going to load data into here off this base address. Then we're going to, what are we going to do? We're going to load some other data into there, and we're going to move it over, and then we're going to store it back in. Okay. That's going to go through all these pathways, and it's going to result in, the key idea here is that these instructions result in some bus traffic. All right, we went through this example. Here's an example of storing data. All the GPOs are going to get some of the data, or some of the instructions. So like the initiator sends the same address to everybody. It's only the device that's responsible for that address is the one the initiator is going to pull pselect high on. Right? So pselect doesn't go high here because this is outside from the problem definition above, that this is outside the address range, so this one should never pay attention. Even though it gets the address, it's just not important. It gets the data too. It just doesn't care. Yeah?
Does the initiator always reads even though key ready is not equal?
You gotta say that real high.
Does the initiator still reads even though key ready is not equal?
Does the initiator read? The initiator will not clock in data until it's told that data is valid. The method for saying that the target tells the initiator the data is valid is by pulling p-ready high. Does that answer your question? Okay. And then it's probably worthwhile to be able to work yourself through this confusing diagram. This is an example of what the simplified block diagram of your GPIO peripheral looks like. Let's see, is there any more to, oh, here we go. Well, in your exam, if you're asked to write the address, to decode the address, you can use a symbol like this, just an AND gate, and just write down what it should decode. It's important to remember that this is hardware that's decoding the address and making a decision off of data bits coming in. If you really want to do bubble logic, that's fine. 32 bubbles is hard for me to read. So that's a method for doing that. But somebody else says, how are you doing the masking instruction in the core? Why are you doing masking? And I was like, oh no, it's hardware that's doing the masking. That's why we're drawing a gate for that. There's some logic to decide if you're reading and writing. The motor here goes and controls that output, either high or low. You could say, I assume high is this, I assume low is that, because we didn't define it. And then in this particular case, you have lots of data buses going back. So there is a mux here because you don't want to have node contention there. So there does have to be some internal mux, even though there's a separate PR data line for every peripheral. It's not, I mean, you still internally in the peripheral, you still need a mux. This is also an example of how one peripheral can have multiple addresses. So each one of these masks for a different address. So the core doesn't have any idea that this all in the same location. It doesn't know that. It just says, I'm putting data into memory, and then all this happens as a result of that. That's the key idea for memory mapped I/O. That the core just thinks this is some block of memory in SRAM. It doesn't know. Yep. Yeah, so we had some slides on it before, and when I introduced this, I probably should have spent more time on it. But basically, motor, GPIO motor, is configuring the output. So you can either be an input, you can be an output, you can be high Z, you can be open drain, open source, all those different things. In this particular example, we just gave one bit. You can be either input and output. And so this is just a noting that it would be either input or output, either connecting these output ports or disconnecting the output port. Does that make sense? Your look on your face says, I don't believe anything you said. Totally fine. Accept that.
Can you explain the pull up and pull down and stuff? Because I'm still.
Sure. Can somebody tell me how pull up and pull down works?
Something like when you're not driving something, if you don't have a pull up or pull down, you're afraid the signal might kind of be floating there. So when you have the resistors that go towards high and low, if you're not driving anything, they'll go towards whichever one of those are connected, because the transistor will
Yeah, that was pretty good. So I think probably the more important thing to, I mean, nothing you said was wrong, but maybe the other part to think about is that half your push-pull essentially looks like this. So this would be open drain, source, gate. Oh my gosh, undergrad. I'm remembering back then. And so if you raise this pin, this is supposed to be a G. If you raise this pin high, then current will flow through here, okay? And you don't have to have a PMOS up here. Like the classic way you do this is a push-pull, so that's an inverter. But you could just connect this to a GPIO pin. And that means if you put current on here, or you put a voltage here, and you open this gain, it's gonna pull current down. If you leave this in high impedance mode, meaning the signal to this gate is low, then it's gonna have high resistance, nothing's going to happen. And so the way you might turn this into something functional is you would put a pull-up resistor here. So this is a 3.3 volts. And this node will so when this thing is open, when the switch is open or the gate is driven low, this thing will pull current and pull this thing up to VDD, or 3.3 volts. But however, when this gate goes high, causing current to flow through here, it's basically gonna give you like 220 milliohms of resistance across here, and is going to bring this very, very close to zero. So this is a way, without having a resistor or a transistor up here, you can put ones and zeros onto this thing. How's that feel?
I think it makes sense. There's like a problem in the practice exam that asks about this.
Yeah.
I was kind of confused why, and it ended up being a
There's slides with fault stat on it that shows you here's how you can go and play with it. You can push all the buttons around and get an intuitive understanding of how loads, pull-ups and pull-downs work.
For the GPIO register, how does it have a 1-bit input on each side of the 32-bit output on each side?
This?
GPIO in the top one.
Well, yeah, okay. Let's just say this is one GPIO pin. This is only a professor made this, a human made this, okay? I'm not a corporation. So this is supposed to represent a single pin. I guess I could have put PB1 or PB0 on here. This is one pin, and so you would concatenate this multiple times to have multiple pins. And so one data line goes into one register in that 32-bit register. Does that make sense? So a better example would have been to have multiple of these concatenated together, and then you could have controlled the entire port.
And that's just for like digital, or so I'm thinking like you can have an analog input off one.
Yes. And so if I had, say this pin, I wanted this to be an analog input, then I'd have to have a mux, an analog mux, that could route it to that register or route it around and go to the ADC. And so then you have to, the ADC is going to be in a different peripheral, then you have an actual little wire that puts that signal over there.
So the idea that our IO pin is either like a logical 0 or a logical 1.
In this example, yes?
And you pull up, pull down resistor, actually make sure that's like the right voltage or.
Oh, no. That's fine. You can configure your GPIO pins to essentially the controller can leave M1 out of the picture, can disconnect it essentially, leave it always high. I guess I should have 2 wires going through here technically. In the real diagram it has that. And so you could just eliminate this from your entire control function and only have it be open drain. So the output register there is going to control this to either suck current in or suck no current in. I feel like that's not the answer you wanted.
No, that has to do with what mode you said.
Yes.
Okay.
Yep.
Can you explain a little bit about mental stability? How does the two flip-flop resolve the synchronous problem?
Yes. It's probably a bigger question. You have to, so first of all, you have to take a few things on faith, okay? First one is that metastability is a problem. Right? We think about digital logic coming in, you put 1 or 0 in there, how can it be anything other than that? Well, if you clock it just on the edge, just on the transition, It may not be a 1 or a 0 on the output just because of the functioning of a D flip-flop. How do you learn about that? Go take 215 or some horrible EE class and they'll excruciating detail teach you how that occurs, okay? And then, so now we have identified that there's a problem. How do you solve it? You put another D flip-flop on there. Why? I don't know. A bunch of engineers did a lot of papers, probably wrote a PhD thesis on exactly why that statistically doesn't cause a problem. In most consumer electronics, you put 2 D flip-flops, except for medical devices. You got to put 3 flip-flops, right? Because that's like the probability is like, 1 in the lifetime of the universe that you're going to have an error. And that's enough for the lawyers. But for all the consumer electronic devices, 2 is enough. So the big takeaway is metastability is a real problem. If you have asynchronous events, like humans pressing buttons could happen exactly on the clock edge, or 2 different clock domains that are not multiple of each other could slide exactly on that problem. The way you solve that is put 2 D flip-flops there. Okay. Yeah.
We're not expected to do like draw a synchronizer if there's like an extra input for an exam.
I think you're getting towards bonus questions, bonus points time if you're starting to worry about that. Well, I mean, you got to see how tired we get as graders and how excited we get when we see something that's right. And we start throwing out bonus points. We try to do it evenly, of course. Or most like the other way is, oh, here's how it really works. Got some things wrong in the problem, but you did some things really well. Okay, so we're a little bit more lenient on grading. That's why it's important as part of this is don't just show the answer. Write in words what your intent is. Give us everything we can possibly grade.
Why was P address bit 7 through 0 on the last slide, and now it's 31 through 0?
Because I took slides together from like different. You're talking here? Where?
No.
Keep going back.
Yeah, this
ISP.
one. Never mind. Okay. I thought it was 7 to 0.
Sometimes you see that. Okay, so address, it's technically you could have a 32-bit address in from the initiator to the targets. However, there are not that many addresses, right? It's just not worthwhile to have a bus that wide. So to save it, they'll actually even make fake, like mock addresses, right? They'll have their own address table in here so that they can reduce the number of wires and make layout easier. It's too hard to explain all that. So we're just going to say, whatever the 32-bit address is from the core is what's going to go on that bus. And from exams and homeworks that were kind of created in the before times when we used that Smart Fusion horrible kit, that was a 7-bit address bus. So that's why, or 8-bit, so that's why you may have seen that from an old exam or something.
The idea is we still like mask the address.
Yeah.
Appropriate target does what it needs.
Yeah. Functionally, it's the same, whether it's 32 or 7 or 8, I mean. Okay. You'll have, this will be on your exam just to remind you, hey, you could have a 32-bit register of D flip-flop. Just label it 32-bit so we know if you're going to use one, or don't label it if you just want us to assume it's 1. Tell us how many numbers are on your buses so that we don't guess. If you put, a single wire into a 32-bit register, we're going to assume you're doing something wrong, so just go and label it. And if you want to concatenate wires together, you can use that. There's your logical 1s and 0s, and here's your and mask symbols. This is more out of just trying to make clear how you communicate to us your knowledge, right? It's not like, oh my gosh, they didn't use a slash at the 45 or 35-degree angle. I'm going to get those guys. It's just like this is a common nomenclature that we can use to communicate through the test.
So go back to the circuit diagram and all the fun stuff. So for being ready, can we just assume that's always going to be VDD?
I'm sorry?
Can we just assume that's always going to be VDD?
When is the one case you cannot assume it's VDD? Anybody from this side of the room, brave person? Some of you even making eye contact with me. Okay, this side of the room. You know the answer. when there's wait states. So say this this register for some reason with something else. So maybe, I don't know, it's an ADC or something that takes a while. The answer may not be ready within one clock cycle. Therefore, you're not ready for the initiator to read the data out of read data. So then you need to hold this low until it's available. Likewise, some reason you might not be ready to clock in the data. I have no idea when that would occur. That seems like a strange example. But when you're writing data, the peripheral could be busy. And then it signals when it's clocked in the data.
So then it's only, if it's only ground when it's in a wait state,
Yeah.
then how do you control that? Or will we have a question that, okay, during this time it's a wait state and we have to say P ready?
Well, you can use any logic you want to control this. It doesn't have to be VD or ground. It can be a D flip-flop. It can be an AND gate. Be creative.
So currently right now it's VDD because we assume that there's no wait state.
Correct. We just assume that could never be a wait state in this toy example. Yep.
If there was a wait state,
What did I put here? What are some ways to hold state for a period of time? D flip-flop. Put D flip-flop on there, put the clock into it. Under some condition, it goes high, passes that thing over. You can make a crude counter, just, every clock cycle it delays by 1. There's lots of little crude counter tricks that you want to do. Say you're on exam and I somehow ask you to make something like a counter or some logic circuit you don't know how to make. Like that one shot that you all had to make on the homework. You could just say, I hope this logic should do this. And at least I can say, well, at least they know what they needed. They didn't know how to get there. But I can give you points for that. If you just random logic, it's hard for me. All right, we're getting to the end of class. We didn't get to the problem. That's fine. We had a good conversation. Any other questions? Yep.
Can I ask you a question about the homework?
Why don't we wait till afterwards? And we can talk about homeworks, yeah? All right, if there's no other questions, we'll let you guys go. There's office hours tomorrow.
I think this is really quick, but this is just for metastability, right?
Correct.
Otherwise, we wouldn't need that?
Correct.
Okay, thank you.
Yep.
I think you went over this, but I might have missed it.
No worries.
The inputs to these 32-bit registers,
Yep.
are there 32 inputs
Yeah.
because of the 32 outputs?
Yeah.
And are they all from I/O, like various
Nope,
I/O?
only the 0th is.
So then where's the rest of it from?
I didn't draw them.
But where does it come from? Like,
So say there's another GPIO pin. So pin 1 and pin 2 and pin 3, and those would run wires over to here. It would be denoted, brackets 1, brackets 2, and then you concatenate them all to show me that they go into there.
so is this circuitry purely what defines a GPIO pin, and the rest of it is to control all of
Yes.
these pins in a set?
Essentially, if we had a slide a couple times when we looked at the real block diagram that's really in there.
Yeah.
That it shows you all the logical elements, and so there's other things in there as well, like there's a hysteresis block and there's like muxes and like all this sort of stuff. So if you want to get a little bit more detail, go look at that example.
Okay, cool, thank you.
Yep.
I wanted to ask about, that's why when I closed it, this
Where's a 1? That's not a 1.
Oh, it's
In my world, because I'm a cranky, I don't tell people. I used to be electrical engineer, so I got a degree. Okay. This next to a bus. This little hat thing always means VDD. This, a diamond shape, or can be that means earth ground, which is slightly different. This means ground. This is an invalid symbol in my world, because some people say that is VDD. So that's the ground shape upside down. That's confusing.
Oh.
And this, some people say this is VSX. Like, that is the VDD symbol upside down. And when you get to CAD and those sort of things, sometimes you can spin everything around, so it can be very confusing.